When naming type 2 ionic compound formulas, it's important to understand how you can recognize that a compound is type 2 versus the type 1 that we've discussed in earlier sessions. As you examine the periodic table, zoom in on the transition metal area. Several of the transition metals will form multiple cations. For example, iron, element 26, has the ability to form a 2+ charge or a 3+ charge. Looking at other elements like copper, element 29, copper can form a +1 charge and a +2 charge. The difficulty in working with elements like iron or copper when you're naming them is that you have to figure out which version of the element that you're working with in order to know what the compound formula will be. Let's work out some examples of this. For example, let's say you had a compound CuCl2, and you have to write the name of it. In type 1 naming, this wouldn't have been a problem. We simply would have said it was copper chloride. But now, because copper forms multiple charges, we have to do a little bit of detective work to figure out which version of copper we're working with. To do this, we're going to first look at a charge that we'll always know. That is the charge of the anion. Examining chlorine on the periodic table, you'll notice that it has a 1- charge. Looking at the ratio of copper to chlorine, you see that it's a 1:2 ratio. The total charge that is being added to this compound from chlorine alone is -1 × 2. So we have an overall charge of -2. As with all ionic compounds, the overall charge must equal 0. So what number should we add to -2 in order for it to become 0? The answer there should be pretty obvious. We need to add a +2. Because there's only one copper, all of that +2 charge must come from the copper itself. How do we name it then? That part's actually pretty straightforward. We're going to say the name of the element, copper, and then using Roman numerals, we're going to state the charge of the ion. So this is copper 2, so Roman numeral 2. And then we're going to write down the anion as we have done in the past with type 1. So we change the name chlorine to chloride, just taking off that INE ending of chlorine and changing it to IDE. Let's pull that example aside and try another example. Let's say we had a compound such as Fe2O3. Again, we're going to start by examining the anion, which we will always know the charge of no matter what. Examining oxygen on the periodic table, we find that it has a charge of 2-. There are 3 oxygen anions in the iron oxide compound, and so we're going to multiply those two numbers together to figure out what the overall total charge of oxygen is in the compound. So 2- × 3 is going to give us a -6. Again, knowing that all ionic compounds balance out to 0, we're going to say that 6 plus -6 is equal to 0. So the charge coming from iron has to be equal to a +6. Again, looking at the ratio here, we have 2 irons, and the total charge that it is forming is a 6+, which must mean that if we divide 6 by 2, we'll get the charge of the individual ion. Our charge should be a 3+. If we do the math, 3+ times a 2, that does give us our +6. So our math works out. Naming this then, we say the name of the element, iron. In Roman numerals again, we're looking to name the charge of the iron, so we're going to say that that is 3. And then we're just going to put the anion with the IDE ending, so iron 3 oxide. All right, pulling that off to the side again. Let's do something different. What if we already know the name of the compound and we're trying to write the formula? That's actually probably significantly easier than what we were just doing. So here's a name. What if we had something like cobalt 3 sulfide. The thing we need to remember is that this 3 here represents the charge of cobalt. So we don't have to examine the periodic table anymore to know what the charge of cobalt is. It is cobalt with a 3+ charge. Sulfide is actually sulfur as an anion. And if we examine where sulfur is located on the periodic table, it has 6 valence electrons, and it will acquire 2 electrons to become stable, becoming the anion S2-. To write the formula then, we are going to simply cross down the charges and rewrite that as CO2S3. That is cobalt 3 sulfide. Realize again that the 3 does not tell us how many atoms of cobalt we have, but instead tells us the charge of cobalt. All right, let's do one last example here. Manganese 4 oxide. Manganese can be a +2 or a +4, and I want to show you this example just to kind of show you how sometimes these can be a little bit tricky. So manganese 4 oxide again means we have Mn with a 4+ charge, and oxygen, as we had stated earlier in our iron example, is going to be an O with a 2- charge. Now just looking at that, we have a +4 and a 2- charge. And we can do the crosstown method that we've used in the past for things that are a little bit more complicated, but we should be able to look at this and just kind of see the ratio. So for every 1 manganese, we will need 2 oxygens to balance that out. So MnO2 should be our answer. Now if we do that crosstown method, I'm going to show you how this works a little bit differently. If we do that crosstown method where we're taking the 2 and we're dropping it down to become manganese's number of atoms, and then this 4 becomes oxygen's number of atoms, we would get Mn2O4. And as we've talked about in class, one of the things we need to recognize is that when our subscripts of ionic compounds are divisible by some number, we need to make sure that we go ahead and divide it. So we would have divided both of these by 2, and we would have gotten our actual answer, MnO2. I just want to end with a few examples of how to identify type 2 compounds when you're given a whole bunch of compounds and you have to kind of sort that out. So we're going to start with the easy ones, which are the ones on the bottom. So write the compound formulas from the following names. All you're looking for to see if it's type 2 is you're looking for Roman numerals. So any of these that have Roman numerals, like copper 2 hydroxide, that's going to be a type 2. Iron 3 phosphide is going to be a type 2, and manganese 4 oxide. Up on top, it's a little bit trickier because you have to reference the periodic table. Generally, if it's a transition metal, it's usually type 2, but that's not always the case. In class, we talked about transition metals like zinc that always has a +2 charge, cadmium is always +2, silver is always +1. So we're always going to say that that's type 1 because there'll never be something else. As we're examining these answers here, then we have to look to see, is it a transition metal? Does it form multiple charges? In our first example, we have Cu2S. We already talked about this previously. Copper does form multiple charges, so we're going to have to give Cu2S a type 2 name, which really all we're doing is we're adding in the clarification piece of the Roman numerals to say what charge the ion is. Looking at the next one, we have NaOH. Well, Na is an alkali metal. It always forms a +1 charge. Therefore, that one is actually going to be a type 1 compound, which we've discussed previously. KBr. K is a alkali metal again, so that's a type 1. CO2. Well, that's a type 3, and we haven't discussed that yet in class, so we're going to skip over that one for now. Na3PO4 is a type 1. IF5 is a type 3. FrCl is a type 1. SnSO4 Sn is tin and it forms multiple charges. So here's our second type 2 compound. Skimming along through 9 through 15, I'm just going to point out the ones that would be type 2. Again, you can find that by looking at the periodic table of elements, looking at the transition metals, and seeing whether or not the transition metal itself forms multiple charges. If it does, it's type 2. So 11 would be type 2. Iron's always going to have to be clarified with the Roman numeral. And nickel. Nickel is also a transition metal that forms multiple charges. We'll always have to clarify what version of the element we're working with. I hope that helps a little bit to clarify what we've been talking about in class. Again, have some patience with this. The more you practice, the easier it actually does become, and easier it will be to recognize a type 1, a type 2, a type 3 compound when they're all scrambled up in the same chemical reaction.